Hey guys, today we're going to be starting the physics unit, which is the third unit of this course. It's longer than the last unit. It's probably more similar in length to the chemistry unit, and there's going to be a lot of math in this unit, so make sure that you have a calculator with you. So in this introductory physics lesson, we're going to be going over different ways that we describe motion and some basic calculations. So some of the terms that you'll need to know are speed, acceleration, velocity, direction, and displacement. You also need to know the difference between scalar and vector quantities, and then do some calculations. Significant digits or significant figures are just a way of determining how many decimal places you need to use. To be completely honest, I don't care if you know your significant digits or significant figures. I would say just keep, 3 or 4 decimal places as you're doing your calculations, and then round to 1 or 2 at the end, okay? Scientific notation is important. It's a way that we represent really, really small or really, really large numbers without having a bunch of decimal places. So the way that we do this is we move the decimal place so that we only have one non-zero number in front of the decimal place. And then you usually keep 1 or 2 numbers after the decimal place. And then you write times 10 to the power of however many decimal spots you have moved. If the exponent is positive, then that is a large number that you're dealing with, so you have moved the decimal place to the left. You would move it back to the right to get the original number. If the exponent is negative, that's a really, really small number that you're dealing with, so you originally, in order to create the scientific notation, moved the decimal to the right. You would move it back to the left to get the number that you started with. So before we move on, I'm just going to show you what I'm talking about there. Okay, so we'll just go through a couple examples of scientific notation. So if we have a really large number like this and we want to write it in scientific notation, we would start by putting a decimal spot at the end of our number if there's not already a decimal. Then we're going to move that until we only have one whole number in front of the decimal. I'm going to move it 1, 2, 3, 4, 5 spots. And so how I would then write this is 2.73, keeping 1 or 2 decimal places after my decimal. And then scientific notation is always times 10 to the power of something. And because I moved this 5 places, it is times 10 to the power of 5. Having a positive exponent here tells us that we had a large number which we've made smaller. Okay, so we have moved the decimal to the left. This positive exponent tells us that we would have to move back to the right, so back to the right, to get to our original number. Let's look at another example. So 0.00000039. If I wanted to write this in scientific notation, I would take the decimal place that I already have, and I need to move it until I have a non-zero whole number in front of the decimal place. So I would move it 1, 2, 3, 4, 5, 6 spots to the right. That would leave me with 3.9, and then write times 10. I've moved 6 spots, so it's to the power of 6. But this time, because I have made a small number larger by moving to the right, I have to make my exponent negative. That negative tells me that I would have to move to the left to get back to my original number. So let's try one last example where we start with scientific notation. So 4.26 times 10 to the negative 4. This 4 tells me I have to move this decimal 4 spots. The negative tells me that I need to move 4 spots to the left towards where negative would be on a number line. So I'm going to take that decimal, move it 1, 2, 3, 4 spots, and each one of those empty divots I fill with a 0. So my answer would be 0.000426. And I know I said that was a lost example, but let's do one where we're moving the decimal the other way. So 7.39 times 10 to the power of 5. The 5 tells me I need to move this decimal 5 spots. Because it's positive, I'm moving towards the right, which is where positives would be on a number line. So I'll move 1, 2, 3, 4, 5. Each of those gets filled with a 0. My final answer would be that. Okay, so that's how scientific notation works. If you're using a calculator, the times 10 usually shows up super, super tiny. And if you're using a graphing calculator, it might actually have a capital E, but that capital E just means times 10 to the power of something. So if you're confused by any of that, let me know. But on a tester quiz, you do want to make sure that you don't write an E in your answer. It has to be times 10 to the power of something if it's in scientific notation. Okay, so the physics that we're focusing on this year is the physics of motion. So motion is the change in the position of an object, and that could happen in more than one direction. It can go like down and to the left or up and backwards or whatever. Motion is often categorized as either uniform or non-uniform. Uniform motion means that the object is traveling at a constant velocity. So what that means is that it's going at the same speed the whole time and in the same direction. So for example, if a car is traveling at 80 kilometers an hour due north the entire time, that would be uniform motion. That can only occur if all of the different forces on an object are balanced, which is actually really difficult to achieve in an everyday situation. Even if you put your car on like cruise control, you know, if you come up to like an incline where you're going up a hill, it might take a minute for the engine to like rev up enough to keep you at 80 kilometers an hour or whatever. And so you might drop down a little bit. And it's certainly difficult, like if you just roll a ball across your desk, it's going to slow down because the force of friction is going to slowly overtake the momentum of the ball. So yeah, it is really difficult to keep an object at uniform motion. Non-uniform motion is much more common, and that is when the velocity of the object is changing as it moves. And that could be that the object is changing direction, or that the object is changing its speed, or both. We measure motion in a bunch of different ways. So one of those is distance, which is delta d. Just a little triangle is delta. So delta d is distance. And because of formatting errors, a lot of these aren't showing up, but I'll just go over them. So distance is delta d. Displacement is also delta d, but the d has a line over the top of it. So it's like a d with a straight line over top of it. Speed is a v. So a change in speed would be delta v. Velocity is a v with a line over it. And so that is how the object's rate of change of its position is changing. And then acceleration is an a with a line over it. And that is the change in the object's velocity. And so I'll just write out kind of those different formulas that you'll need. Okay, so again, distance is a d. If it's a change in distance, it's a delta d. Displacement is a d with a line over it. Again, a change in displacement would be delta d with a line over it. V is speed. Delta v is a change in speed. V with a line over it is velocity. Delta v with a line over it is a change in velocity. And a with a line over it is acceleration. Delta a with a line over it is a change in acceleration. Acceleration just describes how either the velocity or the speed is changing. Velocity and speed describe how the displacement and distance are changing. And then displacement and distance describe how the position of the object is changing. So you will have a formula sheet on the testing quiz for all of this stuff. Just so you are aware, you don't need to memorize any of these formulas. So just as a quick reference here, these are kind of the 3 different common formulas that we're going to be using. So speed is a change in distance over a change in time. Velocity is a change in displacement over a change in time. And then acceleration is a change in velocity over a change in time. And as long as the object is traveling in a straight line, you can also do a change in speed over a change in time. So you may be wondering, why do some of these symbols have a line over top of them and some don't? And it has to do with whether or not these are scalar or vector quantities. So scalar quantities describe magnitude, so how much speed or how much distance, but they don't describe the direction of the speed or the direction of the distance traveled. And so we don't put arrows on top of them. So distance and speed are both scalar quantities. So is time, because time describes the amount of minutes or the amount of hours, but you don't say, I traveled 60 minutes into like north. It doesn't have a direction attached to it. Mass is also a scalar quantity, because when you're describing that something has a mass of like 30 pounds, you don't have a direction attached to that. Vector quantities, on the other hand, include both magnitude, so the amount of velocity or the amount of displacement, and the direction. So you would say like, I traveled 3 kilometers east would be a displacement, because it includes both the 3 kilometers, the magnitude of the displacement, and the direction of the displacement. Those are the ones that have the little lines, sometimes drawn as little arrows over top of the symbol. Examples include displacement, velocity, and acceleration, as well as weight. So weight and mass are often used interchangeably as far as terms go. But mass is like what we think of when we say like, I weigh 130 pounds. We're actually describing the mass, not the weight of the person. Weight is actually measured in newtons. So it's a downwards force. And the reason it is a vector is because weight is always downwards, whereas mass, again, doesn't have a direction. So usually when we're describing vectors, we do use like compass direction, so north, south, east, west, that kind of thing. You can also use angles to describe that. So you might say like that you like moved like 45 degrees clockwise or something like that. We are this year mostly going to be using the compass directions, though if you take physics 20 and 30, you might use more angles. Also, usually north, east, up, and to the right are considered positive vector directions, while south, west, down, and left are considered negative vector directions. And so because of that, you can sometimes have like a decreasing speed, which would be like a negative acceleration, cancel out because of a negative direction. And it's okay if that doesn't make sense to you. That is something that you're going to learn a lot more about in physics 20 and 30. For this year, we are going to consider all vector directions positive. So we're going to ignore the fact that some vector directions are negative. We're just going to focus on all positive directions as far as vectors go. You can still this year have negative speeds and negative velocities and negative accelerations and stuff like that, but we will not be dealing with negative vector directions. We are going to pretend they don't exist until next year. Okay, so we're now going to kind of go through and compare some of these similar scalar and vector quantities like distance and displacement, speed and velocity. So distance, like I said, is a scalar quantity. It refers to how far an object travels. The direction doesn't matter. So for example, John traveled 6 kilometers is a distance. Displacement is a vector quantity because it describes both direction and the amount traveled. And more importantly, it is not the overall amount traveled. It is how far does the object end up relative to its starting point. So you do have to pay really close attention to all of the different directions that an object has moved so that you can compare where it ends up to where it started. So let's work through an example of this. The example at the bottom there says Monica travels 2 kilometers north, 3 kilometers east, 1 kilometer south, and 2 kilometers west, and then another kilometer south. So you might, for those of you that don't just have it visualized in your head, want to draw out a quick compass, so north, east, south, west. And then I'm just going to pick a point on the page somewhere. That's going to be the origin. So I draw a point to represent the origin. I'm then going to draw the movement of 2 kilometers north. That is the first thing that Monica does. So I'm just going to draw an arrow to show going upwards is going north, and write that it is 2 kilometers. From there, she then goes 3 kilometers east. This line that is 3 kilometers long should be slightly longer than the 2 kilometer line. Then 1 kilometer south, so from where she just stopped, go back down 1 kilometer. That should be about half the length of your 2 kilometer line. Then 2 kilometers west, so back this way. Again, this line should be about 2/3 of the length of the line above it. And then 1 kilometer south, so back south again. Notice these two 1 kilometers should be the same length as this 2 kilometer. So, I mean, you could use a ruler to do this if you wanted, and each kilometer could be like a centimeter, or you can just eyeball it like I just did, but you don't want to be like completely inaccurate either, okay? And the reason for that is that if I am finding her distance, the direction of these don't matter. In order to calculate the distance, I just add up all of these numbers. So a 2 plus a 3 plus a 1 plus a 2 plus a 1, 5, 6, 7, 8, 9 kilometers is her distance. However, if you are finding the displacement, you are finding the distance, as like the crow flies, the direct distance between where she started and where she ended up. So this length right there is all that her displacement is. And so if I look at that, I can say, okay, this distance that she is away from her original starting point is the same as this distance right here. And because this entire line is 3 kilometers, and then she came back for 2 of that, the remaining bit right here must be 1 kilometer. And so her displacement is just 1 kilometer. Okay, let's try a second example. Okay, in this second example, Gijik travels 3 kilometers west, 1 kilometer south, and 1.5 kilometers east. I've asked you to determine the displacement. So again, I'm just going to start with my origin point and then go 3 kilometers west, 1 kilometer south, and 1.5 kilometers back east. Now to determine the displacement, you need to figure out how far is Giżyk from the origin. So that distance right there. Now, some of you might be saying, well, he traveled west 3 kilometers, back east 1.5, so he is 1.5 kilometers away from where he started. But that doesn't account for this 1 kilometer south that he has traveled. Because this is a slanted diagonal line, you're going to have to use Pythagorean theorem. So to do this, we create a right triangle, like so. That is a right triangle there. I then figure out what the two sides of my right triangle are other than the hypotenuse. So this side right here is obviously the same distance as that 1 kilometer, so that is a 1. And then this side right here is going to be 1.5, since this entire line is 3. This section here is 1.5, so the other half must also be 1.5, since 3, the entire thing, 3 minus 1.5 leaves me with 1.5. And then from there, we set up our Pythagorean theorem. So a squared plus b squared equals c squared. Our hypotenuse is always across from the right angle, so that is what we're looking for. So we're looking for our c squared. Doesn't matter which side I put at the a and b, those could be backwards. And then I'm going to figure out, okay, 1 squared plus 1.5 squared is 3.25. That is equal to c squared. And then in order to get just c, I need to square root that to cancel out the squared sign. The square root of 3.25 is 1.8. So his displacement is 1.8 kilometers. Okay, so that is it for the distance and displacement comparison. Next, we'll move on to speed and velocity. So speed is scalar because it describes how fast an object is traveling, but not the direction of travel. So for example, the car is going 110 kilometers an hour. That is a speed. Velocity tells us how fast an object is traveling and the direction that it's traveling in. So for example, the car was traveling at 110 kilometers an hour north. Both of these are measured in distance over time. So for example, kilometers per hour or meters per second. And then with the distance attached if it's the velocity. These are just kind of describing the different formulas. Again, we already went over that somewhere over here. So your speed formula is change in distance over change in time. And anytime you see a delta sign, that always means the second minus the final. So that's what this is showing here with the D2 minus D1 and D2 minus T1. When you see this delta D, that just means the second distance minus the first distance. And same with the delta T, that just means the second time minus the initial time. Okay, so that's just what the delta sign means. It's always the second or the final amount of something minus the initial amount. And then yeah, velocity is the same, but you're using displacement instead of distance. Okay, so let's try a couple calculations. I will do the first one of these together with you, and then I want you to try the next two on your own. Okay, so it says during a play in a hockey game, the puck is shot from the center line into the net 17 meters away. The puck takes 2.4 seconds to reach the back of the net after being shot. What is the average speed of the puck? So because it's asking about speed, we will do speed, which is v, is equal to our change in distance over our change in time. Now the change in distance is that it started 17 meters away and ended up in the net. So it has moved 17 meters. And then the time that has passed is the 2.4 seconds. So we would just divide those. 17 divided by 2.4, type the wrong number in, 2.4 is 7.08. And this is measured in meters per second because the 17 was in meters and the 2.4 was in seconds. Okay, so try the next two on your own. Just pause for a second and try them and then come back and get the answer. Okay, so for this one, the bullet is traveling at 720 meters per second. So once again, it has given us a speed. So we're dealing with speed again. And it wants to know how long does it take to hit a target that is 3,240 meters away. So we're given the speed, we're given the distance, we are asked for the time. So we're going to start with the same formula we used last time. This time we are just solving for a different variable. Now remember, anytime you have a fraction like this, whatever's on the bottom needs to be the thing that moves to the other side. So we are going to multiply by a change in time to get that to cancel out. And then of course we must do the same to the other side. That leaves us with 720 times a change in time equal to our distance. And then in order to isolate our variable, right now it's multiplication, so we will use the opposite operation and divide by 720. And that will give us 4.5. And the way that we know what our units are going to be, we look at our speed, which was in meters per second. So this must be 4.5 seconds. Okay, so this last one is actually a little bit tricky because of the units that I'm using here. So I said a slapshot travels at 94 kilometers per hour. If it takes 0.6 seconds to hit the goalie, how far away was the shooter when he hit the puck? Now, as you may have noticed, I am using kilometers per hour as my speed and seconds as my time. And the hours and the seconds obviously aren't the same unit for time, and they need to be. So our very first step here, as you can see, I've already plugged in my 94 kilometers per hour for the speed. I know that I'm going to be solving for distance, but before I can plug in my delta t, which I've put two triangles in front of for some reason, I need to convert it to hours. Alternatively, I could convert the 94 kilometers per hour into seconds. But the reason I'm not doing that is because it's easier to convert something that just has one unit, like seconds, as opposed to something that has two units, like kilometers and the per hour. So to do that, I will just say, okay, there are 60 seconds in 1 minute. So if I have 0.6 seconds, how many minutes is that? And so if we cross multiply here, I get 60 times x equals 0.6. And then of course divide by 60 in order to get the x by itself. So 0.6 divided by 60 is 0.01 minutes, since minutes is what I was solving for. So this is just setting up proportions just like we did in grade 9 math. Just make sure your units are lined up with each other. So your seconds should be lined up and so should your minutes. Now that I have minutes, I'm going to say, okay, I know that there are 60 minutes per 1 hour. So 0.01 minutes is how many hours? And once again, cross multiply, which gives me 60x equals 0.01. And then divide by 60 to isolate for x. Which is 0.00016 repeating, like so. So that is going to be the change in time that I plug in. So I will go back to this formula up here, plug in my change in time. And now to solve for my change in distance, I of course just multiply by whatever's on the bottom here. Do the same to the other side. And you should get as your final answer 0.0156 repeating as your change in distance. Now that is going to be in kilometers because your speed was in kilometers per hour. So if you wanted to convert that into meters, you certainly could. You can use King Henry drank milk during Christmas Mass. To go from kilometers to meters, you just move your decimal spot 1, 2, 3 spots to the right. So 1, 2, 3 spots to the right. Your answer would be 15.6 repeating meters is your change in distance. So either of those would be correct answers, though you do want to make sure you know how to do a conversion like this in case it was a multiple choice question where this was the only answer, or if I specifically asked for the answer to be in meters. Okay, I think I'm going to save that one for you guys to practice on your own. Actually, no, I should just do the whole thing. Ignore me. Okay, let's go through how to do all of these. Okay, I'm going to start by drawing out a little displacement diagram for what's happening here. So the jogger is running 500 meters to the north, then turns around and comes back 300 meters. So the distance is just going to be 500 plus 300, which is 800 meters. The displacement is this distance right here. So they went up 500 meters, back by 300. If we just subtract those, we get a displacement of 200 meters. And then for the average speed, so speed is our change in distance over our change in time. The distance we already calculated is 800 meters. And the change in time, some people subtract the 2 times that you're given here, the 150 and the 100 seconds. But the change in time is actually like after they're done their full 800 meter run, it has been 250 seconds. And before they started, 0 seconds had passed. So really the change in time is 200 minus 0. And get that 200 by just adding the 150 seconds and the 100 seconds. So 800 divided by 200, which I think is 4. It's terrible that I don't trust myself to do that in my head. Yes, it's 4 meters per second because they were measuring their distance in meters and their times in seconds. And then for the velocity, that is a change in displacement over a change in time. So their displacement, we already calculated, was 200 meters. Again, the change in time is that total 200 seconds that went by. So their velocity is actually just 1 meter per second. Okay, acceleration is the last kind of big calculation that we have to get through today. The acceleration is the rate of change in velocity over time. And if an object is traveling in a straight line, you can also calculate acceleration as the rate of change in speed over time. So essentially, it's how much is an object speeding up or slowing down over time. It does need to include direction technically, though a lot of the time on tests and quizzes and stuff like that, if it's like multiple choice, I will just be asking for the magnitude of the acceleration. So that's like the amount of the acceleration or the number without the direction attached to it. It is measured in distance per time squared. So for example, meters per second squared or kilometers per hour squared, stuff like that. And the formula is a change in velocity over a change in time. Remember, anytime we're doing a change in something, it is the second minus the first. And this becomes most important when we're dealing with acceleration because you are always going to have two different velocities or two different speeds. And you need to make sure that you're subtracting the final speed minus the initial speed, not the other way around. And that is because positive and negative acceleration is so important. If you have a positive acceleration for us this year, because we're assuming that all directions are positive, if you have a positive acceleration, it means that your object is speeding up. If you have a negative acceleration, it means that your object is slowing down. Again, here it says like slowing down while going forwards or speeding up while going backwards. That would be like because of the negative directional vectors, which again, we are ignoring in Science 10. You will deal with that in Physics 20 and 30. So as far as we're concerned this year, positive means speeding up, negative means slowing down. So if you're doing a calculation and you forget which way you should be subtracting your velocities, just double check. If the object is slowing down, you should get a negative answer. So let's practice some of these calculations here. Okay, so in the first example here, it says a cheetah goes from standing still to running at a speed of 19 meters per second north in 2 seconds. What is the cheetah's acceleration? So my formula for acceleration is a change in velocity over a change in time. So in this case, it's the velocity is that the cheetah ends up going at 19 meters per second. It starts off going 0 meters per second because it's at a standstill. And this happens over the course of 2 seconds. So we just do 19 divided by 2, which is 9.5. And because we were measuring this in meters per second, and again in seconds for our time, our final answer is in meters per second squared. Okay, for the second question, it says a bike is traveling at 3 meters per second east and then speeds up to 5 meters per second east. The acceleration is 2 meters per second squared. How long does it take to accelerate? So we're going to use the same formula. It gives us the acceleration is 2 meters per second squared. And it also gives us the two different velocities. So the second velocity was 5. The initial velocity was 3. So we do final minus initial. And it wants to know how long this took. So that gives me 2. 5 minus 3 is 2 over delta t. Of course, whatever is on the bottom of the fraction needs to be the thing that moves. So I multiply by delta t. And what I do to one side, I must do to the other. So that leaves me with 2 times delta t equals 2. And then to isolate our variable, I divide by 2, which leaves me with 1 as my change in time. And because we're dealing with meters per second and meters per second squared, my time is in seconds. Okay, this is the last question that we're going to do today, and it is a bit of a tricky one. So a roller skater slows from 8 meters per second to a stop at a rate of 3.7 meters per second squared. If they start slowing 2 seconds after seeing the family of ducks in their path, how long after seeing them do they stop? So I have speed, and stop is also a speed, it's a speed of 0. I have my acceleration, which I can recognize because it has the little squared sign, and I've got a time. But it's also asking for a time. How long after seeing them do they stop? And so there's a couple different ways to solve this. I'll go over what I think is probably the easier way of solving it. So I'm going to start with my acceleration formula. So acceleration is a change in velocity over a change in time, or a change in speed, like we're given here. We're just going to assume that they're traveling in a straight line. So the acceleration is 3.7 meters per second squared. Just so you know, guys, I don't care if you write in your units as you're going, but your final answer needs to have units. My change in velocity. So first of all, sorry, that needs to be negative. Negative 3.7 meters per second squared because they are slowing down. And the reason it needs to be negative is because my final speed is 0 because it's a stop, and my initial speed is 8. So I have to do 0 minus 8, not 8 minus 0. That's going to be a negative number. That's what my answer is, a negative number. And then even though I am given the 2 seconds here, I'm just going to write my delta t because I am looking for time. And that'll just make this easier to deal with for the moment. And then, just like we did last time, I do need to isolate that delta t by moving it to the other side. I'm just going to simplify the top here first. So negative 3.7 equals 0 minus 8 is just negative 8 over delta t. And then, of course, I have to multiply by delta t because whatever's on the bottom has to be the thing that moves. That is like the most common mistake that I see in grade 9 math, in grade 10 math, in this unit in Science 10, even in Chem 20. People don't remember that the thing on the bottom has to move, even if it's the variable. They want to like multiply by negative 8 here. So try to remember that. Anyway, what I do to one side must do to the other. So that gives me negative 3.7 times delta t equals negative 8. And then, of course, to isolate my delta t, I divide by my negative 3.7. So negative 8 divided by negative 3.7 is 2.16 seconds. But it didn't ask for my delta t, which is my total change in time. It already gave me one time, which is 2 seconds, and it wanted to know how long after that they came to a stop. So my change in time is what I just solved. But remember, that is t2 minus t1, second time minus initial time. And so t2 is what I'm looking for. t1 is the 2. And I have to isolate t2. And so in order to do that, I would add 2, 4.16 is my t2. Okay, so just remember, anytime you solve for a delta t, you're just doing the final minus the initial. I was given the initial, they start breaking after 2 seconds. I solved for the delta t using my acceleration formula, and then I can just isolate for t2. Okay, so there definitely can be situations on a test or a quiz where you're not just asked to solve for delta t or delta v or whatever, you're asked to solve for just like v1 or t2 or whatever. So make sure that you know how to do that. The easiest way is to do it in 2 different steps like this, where first you isolate the delta variable and then solve for either the t1 or t2, whichever you're asked for. You could definitely plug in t1 minus t2 in here and have, like, instead of having a delta t here, having t2 minus 2. But it is just a lot more math you have to deal with. You'd have to distribute this into the other brackets. This is definitely the easier way to do it. If you want me to go through the other way, just like email me or ask me in class and let me know. But I don't want to confuse everyone. Okay, that's it for today.